Hi, this is Alejandro Lampropoulos from WorldSensing, and I'm going to describe the DoSSensing, which is the denial of service jammer detector developed for the CIPSEC project. Nowadays, a lot of devices communicate using wireless communications. Pretty much everyone has a cell phone or a laptop and a lot of other different devices that communicate wirelessly. The main problem of the wireless medium is that it's accessible to everyone. This could be an advantage, but in security aspects is pretty much a drawback, and we always need to have take into account different aspects regarding security for these types of communications. So the main issue here is that if A wants to transmit something to B, they need that the medium is idle. If it's not idle, then we have different types or different methods to communicate, waiting for the channel to be idle or transmitting in different frequencies. But what is jamming? Jamming indeed is the fact that we do not allow sender and receiver to communicate by different means. And the most simple one, and is the jammers that we're going to treat here, which are the constant jammers, are the ones where we occupy the medium for a long time. The idea is to produce noise so loud that you cannot even talk with the other party. So the idea is if A wants to send something to B, then they will not be able to receive the packet because the noise is too much loud that they cannot even interpret it. Think about it as two people speaking, and if A wants to talk to B, they just speak as loud as they need in order to communicate. But what would happen if a third party comes and starts shouting so loud that the two people speaking cannot listen to each other? Then they will not be able to communicate. So this is the type of jammers that we want to treat here. It's constant jammers that start making such a loud noise that the medium is occupied all the time and no other communications can be done. The wireless medium is subject to this type of attacks, and it's important to at least be able to identify them because they can harm a lot wireless communications. So the problem is also that we can find this type of devices, the jammer devices, very easily and buy them over the internet. They're not very expensive. We can buy some simple jammers that can reach up to 20 meters for $120, even more powerful ones for $500. And it is, although it is illegal, of course, to use this type of devices, they can be easily purchased and actually used, and the fact that we cannot identify those type of attacks easily makes it a very good way to prevent wireless communications. So what types of constant jamming techniques do we know? We can identify 4 different types of constant attacks in the state of the art. So one of them is the continuous wave. Continuous wave is just a sinusoidal narrowband signal that is emitted in a constant frequency. So we concentrate in a narrowband signal a lot of energy, and we prevent that frequency from communicating wirelessly. Then the frequency modulated is the one that sweeps over different frequencies in the service band. Also, we have pulsed signals. The pulsed signal ones are the ones that are easier to find actually in the market, and they sweep the whole band using intermittent signals with several harmonic components. So the idea is to occupy all the band, making pulses with enough energy so that the noise is too high that we cannot communicate. As we said, these are the ones that we have found and we have bought and we have tested mainly. And the wideband are similar to the previous ones, but they are concentrated in a certain band of frequencies. So these, as we said, these jammers are constant jammers. They just emit all the time. They can be stopped and reinitiated, and what they do is to attack the physical layer. They don't care about any MAC protocols because they just affect the medium. They are not emitting packets that will be received by any of the parties that are talking, that are communicating among themselves, because what they just do is noise. So in critical infrastructures, we have different types of wireless communications with different protocols. As we said, these type of attacks are protocol independent. So, and they could be done in any frequency of the spectrum. So we need to take care about those attacks in the physical medium. We don't care if they are preventing communications over BLE, ZigBee, or LTE, narrowband IoT. We will just focus on the physical layer, so the type of signal that is being emitted and the power of the signal, and not necessarily what kind of protocol they are affecting, because they could affect any protocol at any frequency. So some practice examples about jammers, what jammers can do. A jammer can prevent a cell phone call, for example. It can prevent your computer from communicating. It can prevent a GPS from getting a correct location, freeze your wireless cameras, etc., etc., etc. You can imagine a lot of different examples from preventing a wireless communication. So in hospitals, for example, we can have different types of machines, different types of devices communicating wirelessly. Even some devices we have observed that they need, they can be even decalibrated. They can lose calibration because of wireless signals emitted in a very strong and powerful emission. Something else in trains, for example, different devices like GPS, satellite communications. We have wireless everywhere. So imagine that preventing wireless communications can be very harmful in different infrastructures, even in critical infrastructures where it's actually critical. So what is the solution? What we propose as a solution is a device, an intelligent device called DoSSensing, and a platform. So our device is a sensor, smart sensor called the jammer detector, and we have the DoSSensing, denial of service sensing platform, which is cloud software or in-house software that allows you to interpret the data coming from the sensor and refine it. So what we will do is that the sensor analyzes the physical layer and detects these types of jammer by analyzing the shape of the signal that it's receiving, the power of the signal. It will detect that there is an attack or that there is a potential attack, and it will communicate that to a user, and it is actually also integrated with the XLCM from the CIPSEC project. So basically, the monitoring tool that we will use for the jammer attacks has the following specifications: reliability to up to 98%. It's used real time, which means that it will be analyzing the spectrum in a passive way, which is actually important too. We don't affect the medium, we just listen to the medium. This sensor only listens and analyzes and communicates something to a backend, and it can protect any protocol depending on the frequency where it's set. So you should be able to set this to different frequencies, and it will be useful for any frequency, so it will be able to protect any protocol at different frequencies. So the idea to see it graphically is the jammer detector will be working and analyzing in time, real time, if there is a jammer or not, if there's an attack or not, and it will tell us the power of the attack that it's detecting over time. If there's nothing, it will show nothing over the time, so zero, an attack with zero power. But if there's a jammer, it will detect the interference and show an increase of the power of the detected jammer up to the number of jammer to noise ratio units that it uses. So the idea is to have a wireless jammer detector being able to listen and detect the 4 types of attacks that we have already explained. We have that the tool, the platform, allows us to log the different types of attacks that were found with its power, so jammer to noise ratio, with its timestamp, and with its frequency, where in what frequency it was detected, and the type of jammer, and to communicate that via syslog with the XLCM solution from Atos. Then that it will be configurable. Actually, it is currently optimized for the 2.4 GHz band, but it is possible to use it in different frequency bands from 1 MHz to 6 GHz. Portable, you can take it anywhere, connect it to the internet, and it should be just plug and play. Connect, and it should be just in a couple of minutes sending the data that it's receiving, I mean all the decisions that it's making, if there's a jammer or not, to our backend. So talking about the general architecture, entering into the technical detail part, so we will have a sensor, right, that is composed by an antenna and an SDR module. The antenna will receive the wireless spectrum in an analogical way. It will communicate it to the SDR module. The SDR module will transform that analog data to digital samples, and those samples will be received by the processing board, which will process those samples, that digital data, to come up with a decision. That decision is about if there's a jammer or not at the present time. So as this is real time, that process has to be done periodically, all the time. So what we will need is a processing board that is as powerful as possible, so that it can process all the samples coming from the SDR module, which will be millions and millions per second, and so that it can produce a number of decisions per second. Then that is the part that corresponds to the sensor, the jammer detector device. Then those decisions that the detector makes will be communicated to the monitoring server, which is the software platform, which actually stores the different decisions that it gathers from the processing board. It post-processes them to refine the final decision, and it allows the visualization tool to show the different detections, the historical detection and real-time detection in a friendly user interface. It also communicates with this XLCM about the possible attacks that it will find. So the solution in terms of the code that is running on the sensor, it can be found, it's actually open source, and it can be found in the link on GitHub, in the link that you see in your screen. So you can see how it was developed and how the different algorithms were developed. It mainly has 2 different processes running on a Linux based board, which is actually an embedded Linux. It uses an SDR module for the in our case for the first prototype, it's a Hacker F1, which connects via USB to an Android C2 module, which is the one that runs as the processing board. So the processing board, as we said, has two different processes. One of the processes is called SDR jammer detector process, which is the one that runs the 4 algorithms, detection algorithms for the frequency modulated, the continuous wave, the pulsed, and the wideband jammers. And it analyzes the digital samples to come out with a decision of which of the 4 jammers are there, or if no jammer is there at the present time. And then there's a jammer message receiver process that gets the final decision and communicates it with an external machine, which in our case will be our backend, so the monitoring server that will refine the solution and store it. So this is the output that we can see at the terminal of the processing board. So on the left hand we have the SDR jammer detector executable, which shows no jammer in the case of no jammer with a timestamp. And on the right hand, for each type of jammer, we also have the decision, which is jammer off in all of the cases, and some data that actually, if the jammer is jammer off, meaning if there's no jammer, that data is actually ignored. But then if we have a jammer, this is the case where the jammer is detected, periodically we will have on the left hand the type of jammer detected. We only detect one jammer at a time, and the frequency at which we found the jammer, the timestamp, the power of the jammer in dBs, and well, and that's pretty much it. On the right hand we have the example consumer of the consumer, which receives per jammer which one was the one detected. In this case you will see that only the pulse jammer on and the rest is off, and in this case that decision will be the one communicated, those decisions will be the ones communicated to the monitoring server. As we said, this is a real-time sensor, this is a real-time software, so we have to analyze a batch of samples, a lot of samples per second actually, and from batches we are going to develop a final decision, and we're going to communicate that decision to the monitoring server. We will communicate at least 4 decisions per second, so this is how we manage to run a real-time decision maker. Well, more in detail, one of the jamming attacks algorithms, the pulsed one, you can see that actually it has several steps. It grabs a set of samples, and from that set of samples firstly computes the noise floor, because we need to estimate the power of the noise. We are going to detect jammers up to a threshold over the noise, so if they don't go up through a certain threshold, we do not consider them jammers either. Then we create a spectrogram, we project to the frequency domain, to the time domain, we compute the mean of measures, we binarize the measures. We do a lot of things from that set of samples to come up with one decision. That decision is there is a jammer or there's no jammer. But the thing is, only one set of samples maybe is not enough to make sure that we are detecting or not detecting the jammer correctly. So in order to refine our solution before communicating it to the monitoring server, we have another decision algorithm, which is called the tongue algorithm. The idea is to set 2 different variables, the A variable and the B variable. The A variable is the one that we set the K counter to. So let's say 5. We set the counter to 5, and if we process a set of samples and we come up with a decision that there is no jammer, we will decrement the counter by 1. So if we reach 0 with the counter, then in that case we will decide that there is no jammer present for that set of samples, for all the samples that allowed us to make this decision. So it could be minimum, it will be 5 sets of samples. So if the variable a is 5, we need to decide 5 times in a row a negative decision to make sure that the final decision is negative. Or what happens if we have a positive decision of one of those sets? So if one of those sets of samples give us a positive decision, then we will increment the counter. So the counter will be going down, down and up, or up, up, up and down, and it will eventually reach parameter b, which could be 15, for example. And if we reach with the counter the parameter b, we will say that there is indeed a jammer present for that algorithm that we are running. So and what happens if we are oscillating between yes and no, yes and no? Then we have another counter which will allow us to say that there is no jammer present because we are just going up and down. So this is a way to, let's say, filter some negative or positive decisions that are not correct, so false positives, for example, and it will refine our final decision. That final decision will be the one communicated with the monitoring server. So once we have everything on the monitoring server will refine the solution, and it will store the detections and the final decisions that it makes on a database. That database can be accessed by our visualization tool, which is the one you see right now. Our visualization tool is a real-time tool. It has dashboards that allow us to visualize the detections real-time. In this case, you can see for the sensor that we have on top jammer detector status. If that one is in blue, in light blue, it means that the sensor is active and working. If it's gray, it's not working. It's actually it's turned off. The sensor will be off. Just on the left from the jammer detector status, we have the total number of attacks, the aggregated total number of attacks, and then just below we have on the left the different counters for each one of the different types of attacks that we can identify, and on its right we have the real-time graphs, real-time charts that give us the power of the jammer detected over time. So this is the case where there is no jammer detected, and this one will be the case where there's a pulsed jammer detected. So we see that the status bar turned red, meaning there's an attack detected. It tells us the frequency of the jammer detected. The total number of attacks counter increases, and the pulse attack also the pulse attack counter increases, and also we have just to its right the frequency of the attack detected. Then we can see also that the green line of the real-time chart goes up too, and it's showing approximately 12 dBs for the power of the jammer through time. Then, last but not least, we wanted to also show the prototype in action. Actually, that photo is from one of our pilots. We create a box for the jammer detector device. The SDR module and the processing board are installed inside, and we have a closed box that actually has an antenna on its front, and it's better to point to the center of a room, because the antenna is omnidirectional and it can see whatever is coming from the other side of the room. It's connected to the internet in this case because we are sending the data to our monitoring software on the cloud, so it's connected via Ethernet because we don't want jammers to prevent us from communicating wirelessly. And we install them as high as possible because it can reach more of the room with as high as it is. It detects better. On the right hand, we have the example of the jammer that we are detecting and that we are testing with. And this is everything that we had to explain for this training session. I hope you found it interesting. Thank you very much.